Hello students, in this video we are going to work out a few problems as from cycloaddition reaction in IIT JAM. Before getting into that, let's spend a little more time to gain a few more informations to approach those problems, the information which are mandatory to approach those problems. Okay, let's take 4 plus 2 cycloaddition. Okay, 4 plus 2 cycloaddition. Okay, I already told you in the previous video, this is thermally allowed but photochemically forbidden. Okay, photochemically forbidden. Remember, this one is called diene and this one is dienophile. Dienophile, and this one is adduct. This reaction has one more name. It is called Diels-Alder reaction. Okay, Diels-Alder reaction. Okay, how the diene should be, how the dienophile should be. In the previous video I told you that diene should be HOMO. I used HOMO of the diene, LUMO of the dienophile. Okay, the diene should be, first of all, the diene should be electron rich. Okay, electron rich. You need to have an electron donating group here, or you need to have electron donating group here. Okay, so overall diene should be electron rich and dienophile should be electron deficient. You need to have an electron withdrawing group. Okay, dienophile. Okay, and second point is diene should be in the cis-oid conformation. What is cis-oid? Okay, diene should be cis-oid conformation. Okay, this one is cis-oid and this one is transoid. Cis-oid, the diene should be in cis-oid conformation, not in transoid conformation. Okay, now before getting into the next step, let's see this problem. Okay. It was asked in 2016, the first question. Read it. Among the following, the number of compounds which can participate in Diels-Alder reaction as diene is. Okay, there are several dienes are given. The one which can be effectively used as, and the diene which can be used, which cannot be used. Okay, the total number of dienes which can be used. That is what we need to find out. Remember, I told you that the diene should be cis-oid. The cis-oid is in equilibrium with transoid. But in case, if we have a diene this way, okay, this is cis-oid, but permanent cis-oid, because it is locked. It is locked, so it is a permanent cis-oid. No equilibrium with transoid. If we get this sort of cis-oid, it is good. It must be very much reactive than this one, open chain cis-oid. Okay, and in case if we have transoid can convert into cis-oid by equilibrium. In case if we have a compound like that, this is a single bond. In case if we have a, okay, remember this is a single bond, okay, one double bond and there is another double bond. These two are transoid, but it cannot convert into cis-oid. Not possible, because it is cycle. So trans-side is locked. So this is permanent trans-side, permanent cis-side, permanent trans-side. Trans-side can be used as dienophile because it can be converted into cis-side. But if it is cyclic, permanent trans-side, it cannot be used in the Diels-Alder reaction as diene. But this one, it is a permanent cis-side. It will be more reactive than open cis-side. Okay. Now let us see this question. You see, look at this one. This is a trans-side, permanent trans-side. Okay, this is trans-side, permanent trans-side, so it can't take part. And look at this one. This is also permanent trans-side. This also cannot take part. And this one, permanent cis-side, permanent cis-side. This is permanent cis-side, permanent cis-side, permanent cis-side, and this also permanent cis-side. Okay, all except these two, all the remaining six, 1, 2, 3. Okay, remaining 6 are permanent cis-side. Okay, so 6 dienes can take part as diene in the Diels-Alder reaction because all these 6 are permanent cis-side. Okay, these two are permanent trans-side and it cannot be used as diene. And come to this one. The order of reactivity of the following compounds with maleic anhydride is 2014. As I told you, okay, all are trans-sides. They can be converted into cis-sides. But this one is permanent cis-side. So certainly this should be more reactive than all the others. Okay. Look at the option where 1 is the maximum. B. So certainly B is the answer. But let us see the others also. I told you that this one, okay, this one can be converted into what? Cis-side. Okay. The diene should be electron rich. Just now I told you. Diene should be electron rich. Dienophile should be electron deficient. So, if we have a group here, methyl group, it is good. Electron rich. It should be more reactive. In that case, this one should be more reactive than this one. Okay, 3 is more reactive than 4. Certainly. But if you look at this one, this is a bulky group. So since this is a bulky group, this prevents this compound to turn into cis-side. This certainly prevents. Okay, it prevents. Even if it turns into cis-side, this bulky group creates a hindrance over here, strain here, so that this planarity of these two pi bonds will be affected. Okay. In that case, this one is very much unreactive, certainly because of these bulky tertiary butyl groups. Okay. So in that case, this one should be the least reactive. Least reactive. Okay. The best is 1, worst is 2. Best is 1, worst is 2. Okay. So option B. And as I said, look at these two. 3 must be more reactive than 4. Is it right? Yes, 3 is more reactive than 4. So option B. Okay. Then let us see the Regio Selectivity. Okay. The Regio Selectivity of Regio Selectivity. Regio Selectivity of Diels-Alder reaction. Okay. What is that Regio Selectivity? You see, as I said, it should be electron rich, connected with the electron rich group. This must be connected with electron withdrawing group. So if that is the case, how can I write this? Can I write this the other way? If I write this way, I should get the product this way. D, E. Okay. If I write the other way, the product is Which one is right? Which one is right? Look at this, children. Very important. This is electron withdrawing group. That means the pi electrons will be polarized. It will be polarized towards the electron withdrawing group. So that I will be getting negative charge here, positive charge here. Here, donation, electron donating group means I should get positive charge here, and this one should polarize this way. Okay? So anyway, near the electron donating group I should get positive charge. Near the electron withdrawing group I should get negative charge. So positive, negative will join. Okay? But here you see, electron withdrawing group, near that I will get negative charge. Near that positive charge. Okay? In that case. And here positive charge. So positive is not possible. Okay? Up to same charges, bond formation is not possible. So hope you understand. Electron withdrawing group, adjacent to that you need to get negative charge. And there positive charge. In the same way, electron donating group, adjacent to that you need to get positive. So positive, negative possible, so bond formation is alright. But here positive not possible, so bond formation is this bond not possible. So this is like ortho. If you assume, in fact it goes through 6-member transition state. Okay, the transition state is like benzene. So if you, in that case I can say that these two are ortho substitutions. Okay, ortho substitution is possible. Ortho substitution. In case, if we assume this one, this compound, okay, make a small variation. Withdrawing group, electron donating group here. Here how will be the case? What will be the case here? Positive charge here, negative charge here, because always electron donating group, it should be adjacent to the positive charge. And here positive, here negative. Near the electron withdrawing group, negative. So negative not possible. Okay, this one not possible. Not possible. Only write the other way. Positive, negative, negative, positive. Now, positive, negative overlap is okay. So in that case, the product is what? D and W. If you look at that, it looks like para disubstitution. Okay, so this is para. Okay, so only two types of substitutions are possible. One is ortho, the other one is para. Ortho disubstitution, para disubstitution. Okay, so this is about regio selectivity. Let's see this question. The product of the following reaction is, okay, look at this, which one? Okay, substitution is at the second position. Substitution at the second position. What is preferred? Para is preferred. Okay. Para is preferred. Where is para here? This is meta, ortho, para is here. So answer is A. Okay, A is the answer. Para disubstitution. Okay, right. And next point is Exo Endo. Exo Endo. Okay, Exo Endo. This is always, Diels-Alder reaction is always endo-selective. Endo-selective. That means, if I write the diene like this, diene is electron rich, let it be connected with an electron donating group. And dienophile, it should be connected with electron withdrawing group. it should be like this. Okay, it should never be okay. So you will get bond formation. Look at the orientation of dienophile. Here it comes below, okay, below the diene, but it goes away from the diene, okay. And this one is endo, and this one is exo. Okay, this is the point I was saying about. Okay, so it is something like a book, closed book. Okay, if you assume a book closed, okay, if this is a book, this is within the book, and if this is a book, W is outside the book. Okay, so this one is X endo and this one is exo. Always endo is preferred for Diels-Alder reaction. Okay. See this problem. The major product of the following reaction is 2018 question. Major product of the following reaction is, always we need endo or exo? Endo. Okay. Look at these products. This is exo. This is exo. Here it is exo. Here it is endo. Here endo, endo, exo, endo. So how should it be? As I was telling you, it should be like this, Diels-Alder reaction. Let me draw this. If it is diene is like that, means dienophile should be E. The same way it should be E. Okay. So the dienophile is within the book. Okay. So exactly under this diene. Okay. That is why it is endo. Okay, the product will be like this. The product will be E, E. Okay. So this can, and there is what? Okay. And this can be written like this. Okay. E, E. These two are endo products, and the hydrogens are exo. Exo. Okay. Endo product. So which is endo here? Okay, product is this way. Which is endo here? C is endo. C is the answer. Okay. And let us see this reaction. Let us see this reaction. What is this one? There is a sulfone, and sulfone is a diene, and this one is, okay, this alkyne is a dienophile. We get some products. What is it? You see, SO2, CO2, Me. The product is, the Diels-Alder reaction goes like this. So product is cyclohexene, CO2Me, CO2Me, and SO2. So next step is this SO2 goes away. SO2 goes away. So we get CO2Me, CO2Me. Okay. So this is product H and this is product I. Count the number of carbon. 6, 7. Sorry, only one CO2. I'm sorry, this one is not there, no. Okay, the product, okay. only COOMe. Okay, 6, 7, 8 carbon, oxygen is 2 oxygen, hydrogen is 4, 5, 5 plus 3, 8. Okay, correct. So this is I, this is I. Okay, here the sulfone is the dienophile. After the cycloaddition is achieved, sulfone goes out as sulfur dioxide and we get an aromatized compound, an aromatic compound. Okay, and look at this one. Identify the structures. Okay, structures of M and N in the following reactions. What is actually happening means amyl nitrite. Amyl means pentyl. Pentyl nitrite. What is the role of this means? It performs the role of NaNO2HCl. That means diazotization. Diazotization. So N2 plus diazotization. What is next step then? Next step is benzene intermediate. Benzene, this is M. Benzene. Here, benzene acts as a dienophile and it reacts with N to give this product. What should be N? Remember? Okay. Could you imagine? So, you need to have a dienophile like this. Okay. So, and in between O is there. So, actually the reaction is supposed to be like this. And in between O is there means O should be this way. Okay. So, you will get this product. So, what is N? N is furan. N is furan. Okay. And let us see the reaction. This one. Write the structures of A to E in the following reaction sequence. What is A? Look at this. I goes away. Here it's the minus charge. It comes an SN2 reaction. So what is A? A is 1, 2, 3. Okay. Oh, I'm sorry. 2 is missing. Yeah? Okay. Let me rewrite. Okay. This is A. A can be simply written again. A is equal to. It can be written this way. Okay. Okay. Same A I have written again this way. Look at this now. Here you have a diene, here you have a dienophile. So a Diels-Alder reaction goes like this. This is what sort of Diels-Alder reaction? This is intramolecular. Let me write it here. This is intramolecular Diels-Alder reaction. So the product is, okay, and okay, this is the product, Diels-Alder reaction. Okay, so this is a Diels-Alder reaction but intramolecular. Diene, dienophile, both are in one molecule. Okay, and next step is what? This is B. This is compound B. What is next step? Okay, this is compound A, this is compound B. Next step is, you see, O's analysis. What is the O's analysis can give? O's analysis break this bond. So you get what? I'm sorry. You you get a compound after O's analysis. Okay, the bond is broken this way. Aldehyde, and here one more aldehyde. Okay. After O's analysis, you get like this. Next step is what? Next step is KOH ethanol. This is Aldol reaction. Okay, Aldol condensation. Aldol condensation means you would be getting the product like this. Okay, two types of. Either first one is reaction, this one anion, and this one is this way. That is product D. Product E is generate the anion here, and it reacts with this carbonyl group. That is product E. Okay, so you can practice those things, but in this reaction, Diels-Alder reaction is a part of a sequence. Okay, and again, it is even more special because it is intramolecular Diels-Alder. Diene, dienophile, both are present in same molecule. Okay, so part of the sequence, our intramolecular Diels-Alder reaction is given. So we need to work out and practice. So in order to achieve answer all those questions, we must be clear with all these reactions, not only pericyclic reactions. Apart from that, O's analysis, Aldol condensation, and many other reactions as well, all the reagents, all the reactions. Okay, so I hope you understand. This gives you an insight of how to approach the questions asked from pericyclic reactions, especially cycloaddition reactions. Okay, if you have any queries and comments, please write down in the comment box, and we'll meet in the next video with some other topic. Wish you all the best, and thank you very much.